Okay, ladies and gentlemen, this is a review for Physics 1402. That's College Physics 2. It may also be suitable for University Physics 2. We're going to balance a nuclear reaction. Here is the problem. We have to balance this equation. 1 neutron plus uranium-235 splits uranium-235. You're given a product. You're getting krypton 92 out, and you're getting 3 neutrons out. So 1 neutron goes in, 3 goes out, and splitting the atom. That's where you get the chain reaction. So the question is, what do you have to put in the blank to balance this? Is part B of the equation or of the problem, is the masses of the things you start with the same as the masses of the things you end up with? Why or why not? What is the change in mass? What is the energy for each uranium-235 split? And what is the energy for each kilogram of U-235 that is split? And convert this to tons of TNT, just to give us an idea of how much this stuff is. Part A, balancing the equation. The nucleon number, the neutron is 1 nucleon, the U-235 is 235. The nucleon number is conserved, so 236 has to equal the unknown nucleon number, the one that would go up here, plus 92 plus 3 neutrons. Well, each neutron has a nucleon number of 1. So you get 236. So what goes in the blank here is 236 minus 95, 92 plus 3. Um, 141. So let me erase this part here and put in 141. The nucleon number is conserved, the upper number. That's the A number, number of nucleons, protons plus neutrons. This is a review question, so this is not an instructional video. So you should have been presented with what the nucleon number represents and what the atomic number represents also. The number of atomic number of protons in the nucleus, or number of electrons in a neutral atom. So the atomic number before is 92. The sum of the atomic numbers, that is, 0 plus 92. That has to equal 31 plus 3 times 0, or 31, plus fill in the blank. Or what goes in the blank is 92 minus 31. Uh, 61. And if we look this up on a periodic table, and I've got a problem here. Let's see. 92, 36, excuse me. It's supposed to be 36 krypton. There we go. I wrote down the number wrong right here. Wrote down the problem wrong. Krypton, the atomic number of krypton is 36. And the nucleon number for this isotope is 92. 92 minus 36 is not 61. It is 56. So what goes in this blank is not 61. It is 56. And if we look up this on the periodic table, we find that element 56 is barium. Okay, so that answers what goes in the blank. The equation is balanced. Now, Part C, is the mass of the neutron plus U-235, is the mass on this side of the equation equal to the mass on this side of the equation? Why or why not? It is not equal, because we will find out shortly. Some mass loss converted to energy. By E energy equals the mass is lost, delta M, times the speed of light squared. I put in some constants up here, by the way. The mass of the neutron, 1 AMU equals this much kilograms. The mass of the uranium, the mass of the krypton. We will need the mass of barium-141, so I'll put that. Mass of the barium, isotope 141, is 140.914411 atomic mass units. And the speed of light, we will need that also. To 3 sig figs accuracy, it is 3 times 10 to the 8th meters per second. So a couple facts that we will need in a few minutes. Not equal. You expect a change in mass. You expect some mass to be lost, and it's converted to energy. Now let's find the change in mass. What is, both, we'll need a percent or ratio of the change in mass. To get this, we will need just the raw change in mass, how much mass changes. So let me get a big eraser tool, get rid of this stuff here. Now, let me just do it this way. This gives me room to work, show my work. So I got all the facts over here, and I can work over here. Okay, change in mass. So the mass before, mass on the left side of the equation just equals the mass of the neutron, which is 1.008665 AMUs, plus the mass of the U-235, which is right there. 235.043299 AMUs. The left side mass then equals, I'll pull up the calculator. Let's see, get it over here. 1.008665 plus 235.043299 equals 236.051964. Now we're keeping a whole bunch of digits because we're taking the difference between two big numbers. And to be precise in the difference, we got to keep lots of sig figs for a while anyway. Mass on the right-hand side is going to equal, well, that's the mass of the barium, which I just wrote down, 140.914411 AMUs, plus the mass of the krypton, which I've written down here, 91.926156 AMUs, plus 3 neutrons, plus 3 times the mass of a neutron, 1.008665 AMUs. So the mass on the right equals, add this stuff up. So clear my calculator, 140.914411 plus 91.926156. Good. Plus 3 times 1.008665 equals. So the mass on the right is 235 point, go back to my calculator, 235.866562. 866562. We lost mass. We went from 236.051964 to 235.866562 AMUs. Delta M would then be the left side mass, take away the right side mass. Go back to my calculator. I can negate this one and then add it to 236.05, 236 point, oops, 0.051964, 051964 equals 185,402, 0, 185. We can round to 185 AMUs. You can keep the other 3 sig figs, 402 AMUs. Let's convert that to kilograms at this time. Let's answer this question. Let's answer part E next. There's this many kilograms, 1.6605 times 10 to the 27th kilograms, negative 27th, excuse me. And a little erase here. Negative 27 kg per AMU. Units of AMUs cancel out, so we ought to get, first I'm going to store this in memory so I can keep it around, times 1.6605 times 10 to the negative 27th kilograms. 3.07. Go back to my calculator. 3.07, 860021. Now we don't need to keep this many sig figs now. Times 10 to the negative 28th kilograms. There we go. And I need to do an erasure to get to clear out some space. So let's get rid of some of this. And I think I can do this. Let's just grab this and move it up. There. Get it out of the way a bit and get rid of some of this. That's one nice thing about computers. We can, there we go. We might not have a whole bunch of whiteboard space, but we can do other things to help us get more space. Okay, so we take this number, the 3.07866, and we multiply it by c squared. E equals delta m c squared. So this is the delta m now. Oops. So the answer to part E is energy equals delta m c squared. Here's delta m. And c is 3 times 10 to the 8th meters per second. Go back to our calculator. Delta m is still in the calculator. Multiply it. Oops, I didn't. Control Z. Oh, I did. Okay. Clear, clear, clear. 3.07. 3.0786. I will keep this many digits. I won't keep all, however many. I'll just keep, this is 5 sig figs. I better clear this out. Okay, I've got this stored times 1.6605 exponential negative 27. That gives me my delta m again, times 3 exponential 8, square it, that's c squared, equals, and convert it to a scientific notation, 2.77 times 10 to the negative 11 joules. Rounded to 3 sig figs. So for each uranium-235 split, we get this many joules by this equation. Okay? Percent change. So we got to take the change in mass, that's this, in AMUs divided by this in AMUs. So let's get that. Memory recall, that's how many AMUs was the percent change. Divide it by 236.051964 equals. So this is the decimal change. It is not the percent change. So I'm going to get rid of some now. Now that I've done the computation, I can get rid of some stuff. Yeah, I've gotten rid of a lot of stuff. I know what delta M is now, so I can get rid of a lot. Clear out my whiteboard space. Erase my whiteboard, in other words. Get rid of this guy. Okay. Now the percent change, there we go, and that would be delta M over the starting mass equals 7.85 times 10 to the negative 4. There it is. That answers this question right here. Now, last point, last question. Energy for each kilogram. Well, delta M over M is this, so you might as well multiply it by 1 kilogram. If we start with 1 kilogram, if M equals 1 kilogram, delta M is going to be 7.85 times 10 to the negative 4th kilograms. Almost 1 gram. And then finally, we can get the energy released. The energy is delta M c squared. And we can go back here. We've got the number in our calculator. Multiply that by 3 times 10 to the 8th and squared equals 7.07 times 10 to the 13th joules. A lot of joules. convert it to tons of TNT. 4.184 times 10 to the 9th joules per ton of TNT. Energy release equals, go back to our calculator, divide it by 4.184 times 10 to the 9th joules, or by the conversion factor. So we've got 16,000, and if we do it out of scientific notation, right around 16,900 joules, 16,900 tons of TNT. I'm rounding. Am I rounding correctly? Yeah, 16,900. I've rounded correctly to 3 sig figs. A lot of energy. 1 kilogram of uranium. A lot of energy. This is a little bit less than the energy released by the Hiroshima weapon. It was dropped at Hiroshima. So that's why nuclear energy is so vast, and this important equation equals mc squared tells us that we have a lot of energy that we can get out of this. Okay, so I'm just cleaning up. I'm erasing my board a little bit. That ends this problem, and we'll go on to the next one.